Okay, I wanted to talk a little bit about the section 1.1 group work activity that we did in class. And just going to go through these 4 screens. So the first screen was looking at these 2 functions. Are these the same function? We talked about this in class, but I want to just gonna review it just to have completeness here. So we did talk about the options of like different ways that you could look at this. You could look at plugging in different values of f and g. You could look at graphing both of these functions. And I'm going to go ahead and actually graph the 2 functions, and I'm going to use Desmos because it is easy and I'm familiar with it. So I can actually copy and paste, especially since this is Desmos displaying it. Copy F there and copy G. Oops. And if I hide and show G, I can see that they are right on top of each other. If I look at F of 3 and G of 3, oops, why are they undefined? Let's think about why they're undefined. It looks like 3 is not in the domain. Sure enough, if I put 3 in here, then that will make put a negative number under the square root. So it looks like x and u have to be less than or equal to 2. So let's go with 1. So they're the same on 1, they're the same on 0, and they're going to be the same everywhere. And one thing is to recognize, like, what is this notation doing here? This notation says the output from a function called f from an input that we call x. Now I can just replace this x with the word input. It says take the input and then add the square root of 2 minus the input. And g says take this input, u, I'm going to call it input, and I'm going to start with that input and then add the square root of 2 minus the input. So whether I call it x or call it u doesn't matter. That's just a kind of dummy name for what I am calling the input to this function. And both of them have the same instructions for what you do to the input in order to get to the output. So yes, they are the same function. Looking at some of the explanations here, as long as x and u are the same value, both functions should produce the same results. Yes, the equation is the same, but the variable is different. And I think this is the class that I noticed that there was somebody that used basically this explanation for both a yes answer and a no answer. Well, it wasn't the same person, but somebody was able... so that they're not the same variable, so they're not the same function. And the other one says, well, they're not the same variable, but they are the same function. So I think one thing that we discussed in class is that it's nice to have, like, this begs for a little bit more explanation of, like, what does it mean that the input variables are named something different. So... so they use different variable, but the form is totally the same. We can put the same numbers in each variable and we would get the same answer. So this is really getting at the heart of like how that formula is really describing a process, and it doesn't really, and there's a reference to the graph here too. So it doesn't matter what the name of the variable is as long as the function is doing the same things. Okay, let's look at the next one. Are these the same function? And we might take the same approach here and ask, are these the same function? Some of you already actually took the time to do some work on paper. And I'm going to do all of this work on Desmos just because I don't actually have an easy way to get paper up on my display right now in this recording mode. So I'm going to go ahead and look in Desmos again. And paste in that f, and I'm going to copy and paste in this g. And, I can do the same thing. It looks like they are the same graph, okay? And some people alluded to, let's see, what was the split on this? More than half said, yes, they are the same function. 16 students said they are the same function. 11 students said they are not the same function. So for yes, factoring out x from the numerator shows that f of x equals x times 1. So you cancel out a factor of x minus 1. So let's actually look at this. And I'm gonna look at, I think some people probably said that you get the same value. So if I look at f of 2 and g of 2, they're the same. And if I look at f of 5 and g of 5, the outputs are the same. They're both 5. What if I look at f of pi? Because why not? Oops, pi times 5. Okay, they're the same. So it looks like they're the same. And if I actually, so this is a little bit of an exploration, and I've checked that they have the same value on 3 different values. The graphs actually show, the fact that one graph lays exactly over the other shows that they have the same output values on infinitely many input values. And so the suggestion from some people is to factor the x out of the numerator of f. Let's actually do that. I'm going to just duplicate that line, and I'm going to take away this because this says I've defined f in more than one place. I have an f here and an f here, so I'm just going to remove that f. And it's giving me a warning that says I need something on both sides of the equal sign. That's fine. I'm not actually using this to calculate anything. I'm just using this to show some of my work. So factoring out an x from the numerator, that would mean this is going to be x times x minus 1. And then this is the same as x times that fraction. Okay, and that fraction is equal to 1. So that fraction is equal to 1. And so that shows that f of x equals x. Okay. So doing this work actually gives us an algebraic justification for showing that f and g are the same for, it seems as though, all values. So this seems to be a good justification for the people who said yes. And let's actually keep going and look and see who says no, if there's any good explanations for that. They do not have the same value. Well, so far we've only seen the same value. They're the same except for the domain is different because x cannot equal 1 for f of x. That is an interesting clue. This one says there's 2 different functions if we want to graph it. I'm not sure. I mean, my graph looks the same, so I'm wondering if this person got a different thing. But this brings up a really interesting point that x can't equal 1 for f of x. So I tried putting in x equals a few different values. I didn't try 1. And here we go. F of 1 is undefined, whereas g of 1 is equal to 1. So this is a very important point, and it's worth kind of noting different software packages. We're using technology to graph these functions, and different software packages do different things when you have what's called a hole in the graph, right? And Desmos does not actually make the hole in the graph visible. And I think this is an interesting question for you to kind of ask, like, why would that be the case? Why wouldn't they actually show the hole in the graph? And one thing that you can do is if I click and hold on a point here, then I can actually drag and see different points on this graph. And if I come up to where 1 is, the input value of 1, it does show me, like, you see that the point becomes an open hollow point now, as opposed to a solid point here. So it does show me that hole in the graph, but I kind of have to know to look for it, which is an indication that, you can't use the technology blindly. You have to kind of be aware of all of the parts of the math that you're doing. You use the technology to aid you in exploration, but that doesn't mean that you get to ignore the algebra here. So when we see this, we should be very alert that we can't have x equal to 1, okay? So it's worth kind of noting that this function here in line 3 is equal to the function in line 4, provided x is not equal to 1. So, in fact, f and g are not the same because they don't have the same domain. F has 1 excluded from the domain, and g has 1 in its domain. So the two functions are equal everywhere except at x equals 1. So they are not equal functions. Okay. So let's look at this one. Let me pause for a moment. To get rid of that little message. Okay. Are these functions? Okay. So let's look at the student view. So select all of the curves that depict y as a function of x. And looking at y being a function of x should mean that x is the input and y is the output. So at each input value, there should only be one output value. This is the idea of a function. A function, like you give it an input and it says, here is the output from that input. And many people saw that this first a is not a function because, for example, at the input of 0, I would see 3 different outputs. So that would be not allowed as a function. And so you can actually look at the vertical line test as a way of determining that. So vertical line actually gives you, basically, it gives you all of the different y values for one particular x value. So that's what the vertical line is. It's x equals some number. And it's checking if you hit the graph more than once, then that means that you're getting more than one output value for that input value. If I run across different x values for graph B, it looks like I'm not going to hit any more than one y value. And for C, the only sticking point might be at x equals -2. But the notation that we use for this indicates that for x values that are just to the left of -2, I'm going to use this lower branch to figure out what my y values are. And that will be true as I get my x values closer and closer and closer to -2. But when I actually get to -2 and to the right of -2, I'm using the upper branch. So that's that hollow dot says this line goes all the way up until all of the values that are less than -2. But once we're at -2, I don't use this point. I use the point up here. So the output value for input -2 would be -1. Okay, so C is a function. Okay, D is not a function because at each of these integer values, I would have, if I put a vertical line through x equals 1, I have infinitely many y values there on that graph. All of the values are included between 0 and 1. So that is not a function there. Okay, so let's actually look at some responses. It looks like most students got, I don't even know how many students there were in this. Looks like 32 students in here. So most students got that B is a function. Most students got that C is a function. Fewer, though. It looks like that little breaking point got to a few people. And a couple students said A is, and a couple students said D is. So it might be worth taking a little bit of time to review that. So domain, graph B domain is x is between -3 and 2 inclusive, and the range is y is between -1 and 3 inclusive. Let's look at this. It said x is between -3 and 2 inclusive, -3 to 2, okay, and y is between -1 to 3 inclusive, and I agree with that. And we could even, write this in interval notation, would be from -3 to 2, and the range would be from -1 to 3, using the square brackets to indicate that that those border points are actually included in the interval. Okay, and for C, it says domain is from -3 to 2. Some people might be tempted to split up that domain here, but basically I can use everything from -3 to 2, not including 2 for this piece, but then including -2, including -2 to 2, that can all be part of the domain. So really I can put any x value in between -3 and 2. So that seems right. You might take a moment to see how you can write that in interval notation. The range, it says the y values should be between -3 and 2, including, -3 and -2, including -2. And the y value should be from -2 to 3, including -2. And I want to see, so y values, I see y values from -3 to -2 here. I don't see them including -2 because there's no y value -2 associated in that graph because of that open circle. So I would actually correct this range to be from -3 to -2, not including -2. And then I will put the union symbol and if I found that from my character palette, but you can also just say union in your work. If don't worry about getting finding symbols in your writing here. I wonder if it's in here. Doesn't look like it. Okay. So union. Y values. So it looks like you might be tempted to say we have everything from -3 to 3 in Y values on this graph, but we don't have any Y values from -2 to -1 on this graph, right? So we have all the Y values from -3 to -2 in this branch, and then this branch covers -1 to 3, all inclusive. So it would be -1 to 3, including both of the endpoints. Okay. This one. So 3 runners competed in a 100-meter race. The graph here depicts the distance run as a function of time for each runner. What all can you say about what happened in this race? If you haven't taken the time to look at this on your own, I think take the time, because I think that while this looks like a simple graph, it takes a little bit of time to dissect like what is actually being shown in this graph. So I'm going to look at some responses here. Person B sprinted in the beginning, began to plateau his speed, and then sprinted again at the end. So I'm wondering where sprinting, like, so person B, that's this bold red graph. So sprinted in the beginning, plateau their speed, and then sprint at the end. Person A started out the slowest, but then had the greatest gradual increase in speed and surpassed person B, winning the race. And person C also increased in speed the entire race, but came in last. And it's worth kind of asking yourself, like, who came in first and who came in last? And what evidence do you have for this? I'm going to look at some more answers. Person A started slow, but sped up to finish first. Person B achieved the fastest speed, but paused partway through, coming in second, and person C kept up a steady speed throughout, but finished last. Okay, so this person said A finished the race fastest and C was the slowest. I think this is consistent with what other people said so far, but it would be nice, like there's a lot of information shown in this graph. So you should take a moment to think about, like, what evidence do you have that person A finished the race fastest and person C finished the race last? This is good, because this one shows they reached the 100 meters the fastest in the least amount of time. And C kept up the same pace from the beginning, and they one of, like, I think this sentence here really gives a big clue. This graph is graphing distance run over time. So that means that A reached that 100-meter mark in the smallest amount of time, in the least amount of time. B reached that 100-meter mark in more time, and C reached that 100-meter mark in the most amount of time. So this is the clue that A came in first and C came in last, is that it took the most time for C to reach 100 meters and the least time for A to reach 100 meters. Also, there's a lot of reference to who's running fastest and when. There's several people who said that C ran at a steady pace. That basically means that it's like the C graph is almost linear. If this was a straight line, then that would be an exact steady pace. And there was some confusion about, like, what B is actually doing here. So is this happening that, like, I think we can all agree that B sprinted here and then sprinted in this last bit. But what happened in this middle part where there's this plateau. What is B doing? Is B running at a slow but steady pace? Or one person actually said that B stopped. Towards the middle of the race, stopped. And so did B settle at a slow pace, or did B actually stop running? And again, we're going to look at what is being graphed here. This is distance run over time. So if this is 40 meters, then B at this point is staying at 40 meters. B is not running at all. B has stopped running at this point and is standing still, resting, and then they are running really fast again. So, I think this is a really interesting example of how much information you can get from a graph. And all of the information that we get from this graph is stuff that we will be looking at over and over and over and over in this class, talking about rates of change, the rate at which these runners are running. This really gets at the essence of what we're studying in calculus. Calculus is about an in-depth study of functions, and saying more about, runner A reached 100 meters after this amount of time, that's one way to say it. But then there's so much to say about how runner A was kind of going very slowly at the beginning and then went really, really fast and then slowed down a little bit at the end. And so, there's a lot being shown in this graph here. All right, I hope this helped. I hope it didn't ramble on too long going through this little exercise. All right.